Let's turn our attention to teaching model number 3. One of the things that you may remember from first year chemistry is not only should we be able to draw our molecule, especially those that have chiral centers in 3 dimensions, we need to indicate which particular enantiomer that we have. A system was developed by chemists Kahn, Ingold, and Prelog in the 1930s, and other scientists adopted this approach, and now it's the conventional approach. I'd like to remind you that a molecule will have no idea if it's being designated R or S. This is a human convention, but we have agreed to take this approach. In similar way, we make the comment that, like a glove, a chiral center can either be right-handed or left-handed. So right-handed chiral centers we refer to as R, after the Latin word for right, rectus, and then left after the Latin word for left, sinister. And the way that we do this is we consider the chiral center and then we prioritize the 4 groups around that chiral center. So remember, in the case of carbon-carbon double bonds, we have stereocenters, and there are 2 groups to prioritize. In this case, our stereocenter is a chiral center, and there are 4 things to prioritize. Fortunately, the method in prioritization is the same. It's simply looking at the atom that has the highest atomic number. And so in our case here, we can easily see that the hydrogen would have the lowest priority, and the chlorine would have the highest priority. Again, you can simply look on a periodic table to see which atom has the highest atomic number. Now, the other groups that are present both have carbon. So we have carbon A and we have carbon B. But you can see that carbon A is attached to 3 hydrogens, whereas carbon B is attached to 1 carbon and 2 hydrogens. So we're looking for that first point of difference. Carbon B has a carbon where carbon A has a hydrogen, therefore, of course, carbon B has a higher priority. So that would be 2, and this would be 3. So the first approach is you need to prioritize the different groups about the chiral center. The next thing you need to do is to make sure that the lowest priority group is going away from you, going behind the plane by which you are looking. And indeed, it's all nicely lined up in this case. And often it is a hydrogen, so hydrogen's going back. And then we simply count. And we see in counting 1, 2, 3, whether we're counting in a clockwise direction or a counterclockwise direction. So in this case, I got a 1, 2, 3. So I can see that I'm counting in a clockwise direction. And indeed, if I'm counting in a clockwise direction, well, then we designate an R. If it's a counterclockwise direction, well, then, of course, it would be an S. Again, this is a human convention, but we all agree to do this. And so, indeed, you should learn to do this as well. So to make sure that you're feeling comfortable in this sort of approach, I ask you to turn your attention to these examples and designate whether or not the chiral center is R or S. Okay, so let's go through some of these examples. Now, I did want to remind you that you can't designate a chiral center as R or S unless it's drawn as a Fisher projection or a perspective drawing, a wedge and a dash. For example, if I draw this butane 2-ol like this, there's no way that you can designate R or S because you don't know which particular enantiomer is being represented. We can still say there's a chiral center there, but we don't know which enantiomer it is. At least at first, you may want to fill in whether or not there's a hydrogen present, and then we'll prioritize. Usually a heteroatom, that is an oxygen, nitrogen, sulfur, any of the halogens, will have a higher priority than carbon or hydrogen. So we'll designate the oxygen as 1, and of course the hydrogen 4. And then on either side of the chiral center, we have carbons. But of course, the carbon here is bonded to 3 hydrogens, whereas the carbon here is bonded to a carbon and 2 hydrogens. Now, you don't always need to write all this out, and soon your brain will just quickly translate the fact that this is priority 2 and this is priority 3. And then I count, and I can see with the lower priority group already going back, I count counterclockwise, and therefore this would be an S. Moving on to molecule B, what's not written on the chiral center is a hydrogen. And then I prioritize. So I've got 1, I've got 4, over here is 2, and here is 3. Be careful. We've prioritized, but our lowest priority group is not going back. So I alluded to this a couple of minutes ago, and that is, recall that if you exchange the position of any two atoms or groups about a chiral center, you'll end up with the enantiomer. So one of the things that we can do is exchange 1 and 4. Now I'm not actually going to move the atoms, but I'm going to exchange the priorities. And the reason why I chose those is I want to put priority 4 at the back. So that's what I'm doing. And I'm putting priority 1 at the front. When I do this, I can then count. And so I count 1, 2, 3. But I'm counting for the enantiomer of the molecule that I'm interested in. So I count and I can see, oh, well, this is an S. Therefore, the original enantiomer would have equaled an R. So do keep this in mind. You need to switch so that the lower priority group is going back, but remember that you switched, you count, you see that it's going counterclockwise, well then the original must have been R. And then in the last structure we have a couple of halogens. I know chlorine has the higher priority, then fluorine, then the carbon. And of course the hydrogen has the lowest priority, and fortunately for us it's going back. And then I count 1, 2, 3 like this, and therefore this has an R designation.